All right, now let's talk about our genetic operators that we're going to use to move our population forward until we find a solution to the problem. So there are several different ones, different genetic operators we're going to use in our genetic algorithm. We're going to use crossover, which models mating, sexual reproduction, where two individuals come together, somehow intermingle their genetic material and produce offspring. We're going to look at mutation, which models biological mutation. So just every now and then, zap, a gene gets changed randomly. And then we're going to look at selection, which models the Darwinian survival of the fittest idea, even though that's really not something that Darwin ever argued for necessarily. That's how it's implemented in a genetic algorithm. So let's start with crossover first. We're going to use what's called single point crossover according to the following algorithm here. And in this situation, we're going to use a variable, a parameter called chi. Chi is the probability of a crossover, so it's a number between 0 and 1. And I usually use 0.6 for my value of crossover. You don't have to do that, but that's just one that has been my habit to use forever. So here's how it works. For every individual in the population, we roll a dice. We choose a random number between 0 and 1. If it's less than or equal to chi, that means we're going to perform a crossover. So chi, in a sense, is your likelihood of mating if you're an individual in this population. So if the random number is less than or equal to chi, then we pick another individual as a mate, and that's y. Okay, so now I have x and y. X is the current individual as I'm going through the population. Y is the individual that's chosen to mate with. And that could theoretically be yourself. It could be X and X. If it happens, that's okay. It won't be a problem. And then in that situation, we select a random gene location. So a point in our example here in that 5 double individual. We choose one of those locations, and then we swap the genes after that location between those two individuals. So this would look like this. If I have an individual here, I'm choosing X is individual 1, so that would be the second individual in the population is chosen to undergo crossover, or that's the first time that the random number generator gives me a number less than 0.6. Y is individual 6. And then a crossover point is chosen to be 0.3. Then after the crossover, this is what the result would look like, right? Just the genes between these two individuals have been swapped. So note that the crossover doesn't produce a child while leaving the parents unmodified. In this situation, a crossover actually produces 2 new individuals that alter the originals, okay? So you just follow that algorithm, and this is the result. Mutation then is also what we call single point mutation, and the parameter there is mu. That's the probability of mutation, so that's also a number between 0 and 1, and I usually use a very small value of mu, 0.01, so there's only a 1 in 100 chance that you're going to undergo mutation. So for every individual in the population, we pick our random number or generate a random number between 0 and 1. If it's less than or equal to our mu parameter, that means I'm going to be mutated. So I pick then another random gene location in that individual and randomly replace that gene with a new value from the same problem domain. So in our situation, the numbers in those genes are values between -10 and +10. And so our new value would be a randomly chosen value from that range. So suppose we're going through and individual 7 happens to be chosen to undergo mutation. So we look at individual 0. No, it doesn't do mutation. 1 doesn't do. 3 doesn't do, etc., all the way down to 7. And that's the first time that check of a random number is less than or equal to mu. Then we choose a random gene location. So that's gene location 2 in this example. Then we pick another value from the range -10 to 10. And just to illustrate, to drive home the idea that these would be doubles and not integers, I'm just going to suppose that the value is 3.4. then that value gets changed there in the chromosome. So mutation doesn't alter an offspring, mutation alters an existing individual. All right, in our next video then we'll start to talk about selection.